Hello everyone, welcome to today's webinar. My name is Mark Clark and I will be your moderator for today. Today's webinar is titled Identify Workload Imbalance and Maximize Application Efficiency and Scalability. This webinar is part of the Optimize HPC series of webinars. Your presenter for today is Florent Lebeau, Solutions Architect from ARM. During the webinar, please direct any questions via the questions panel, and there will be time made for Q&A at the end of the presentation. Recordings for this webinar will also be made available to all those registered for this session. We would also appreciate your feedback, and there will be an opportunity for you to do so at the end of today's session. Also, if you have any suggestions for future topics, please comment in the questions panel. I will now hand you over to Florent, who will conduct today's presentation.
Thank you, Mark. Hello, everyone. This session is part of a webinar series on how to optimize high-performance computing applications. My colleagues have already explored many of the topics shown on this road to performance. If you would like to know more about higher performance killers, many core efficiency, or memory performance, feel free to have a look at our ARM YouTube channel to catch up. Today, I would like to tell you more about workload balancing, its challenges, and how to identify this with our tools. You will see that imbalances can appear in many aspects of your application, and that ARM HPC tools can help diagnose and overcome these kind of issues on all HPC platforms. So let's define what is workload balancing first. Wikipedia defines it as the aim to optimize resource use, maximize throughput, minimize response time, and avoid overload of any single resource. In other words, it aims at avoiding asymmetry between processes having too much work and processes having not enough work. Workload imbalance is a frequent performance issue due to distributed computing itself and the increasing complexity of HPC systems. Parallelism implies aggregating compute power from several sources, which can be x86, ARM, power processors, FPGA, or GPU accelerators. Parallelizing come at a communication cost depending on the locality of the processing elements, whether they are on the same socket or on different nodes, for instance. Eventually, the way the compute domain is split between heterogeneous resources, how it is distributed on the machine, and the nature of the parallelism itself, whether it is data or task parallel, may result in a workload imbalance of some sort. When this becomes the bottleneck of your application, it is important to use the right tools to detect the problem and fix it. Workload imbalance affects all stakeholders of HPC systems. The scientists see their application running longer and generate less results from their allocation time on the machine. The sysadmins see increased demands for hardware resources, while this does not improve productivity. And the system owners get less return on investment from the science generated and increased operation costs. This is not only a developer's problem, but a production system efficiency problem. Let's imagine a simple scenario where an application can be executed in parallel on two tasks or threads. Because of dependencies, synchronization barriers are necessary. This results in some tasks waiting idle for others to complete, which in the end waste computing resource. How can we identify such patterns without investigating the source code? ARM Performance Report is a solution. It is easy to use. You don't need to recompile the code. You can just prefix the execution command in your job script with the perf-report command to generate an HTML report that describes the behavior of your application at full scale. The report gives information about the settings used for the job, for example, the number of nodes and processes, if you profile an MPI application, or the number of threads, if you profile an OpenMP application. It gives you the total execution time of the application in seconds. In addition to that, the summary indicates how much of the time is spent computing, communicating, or performing I/O. Below the summary, users can find more metrics to understand the efficiency of each of these aspects. Advices and guidance are given to help users understand the behavior and take action. Performance reports can find clues that indicate a situation of workload imbalance. For example, when time is spent in MPI collective calls, such as MPI barrier, MPI broadcast, etc., with no actual data transfer, or when threads are stuck in locks, mutexes, and leave CPU core idle. You can see that in those two cases, the tool provides these information and display the hypothesis for poor performance. Now, we successfully identified an application with a sign of workload imbalance, but further investigation on the source code is required. ARMMap, part of ARMForge, is the right tool to investigate this. It only requires the source code to be recompiled with the debugging flag and to prefix the executable in the job script with the map command to generate a profile at production scale. ARMMap is lightweight with very little overhead and generates a profile of a few megabytes even for large jobs. The profile can be opened afterwards in the GUI, as you can see on the screenshot on the right. The GUI displays the application activity per process for MPI applications, or per threads for OpenMP applications, in the timeline on top of the GUI. The color specifies the kind of activity: green for computations, orange for I/O, and blue for MPI communications. The source code in the middle is annotated with activity information. It becomes very easy to understand what kind of activity is performed. At the bottom of the GUI, a summary of the top functions and call stack is also provided to the user in order to identify the bottlenecks easily. Let's profile a simple application that shows many imbalance issues. On the main thread activity on top of the GUI, we see here that for the main bottleneck, half of the processes are performing computations, when the other half are performing MPI operations. This is a typical sign of imbalance. Selecting a time frame where this occurs enables us to better understand what is happening in the source code. You can see that the source code is annotated with time information, but not only that, it also shows where time is spent in the selected time frame and what operations are performed with the same color code than in the main thread activity above. As a result, we understand that 4 processes out of 8 are computing values of an array where the others are waiting in the MPI barrier call. Additional metrics, MPI metrics, underneath the main thread activity confirm that behavior. For each metric, a graph draws the minimum, maximum, and average value. Shading is used to display the standard deviation of the distribution. We see that the MPI call duration metric shows that half of the processes are waiting idle for 15 seconds until the end of the MPI barrier call, when the CPU memory access metric shows that the others have finished retrieving the data from the system memory to compute results. This information is also given in the breakdown window, which displays the behavior per line of code instead. Selecting line 111 show that 90.5% of the time spent on that line correspond to system memory accesses operations. Optimizing imbalance issues can be difficult. Does it happen because of the operations performed do not have the same costs? Because more data is given to some processes than others? Because retrieving the data is more costly? MAP can help answer these questions, looking at how the other processes are accessing data from the same array on line 120. We understand that only 61% of the time is spent accessing the system memory. It looks like we've pinpointed the reason for the imbalance. Half of the processes spend less time accessing the system memory and spend more time vectorizing instead. This thanks to contiguous accesses to the array, which allow good usage of the cache memory. The other half of the processes perform strided access instead, responsible for the high number of memory accesses. As a result, they spend more time computing, causing the first 4 processes to wait for them to finish. This is one of the few imbalance issues of this example solved. Now, another typical issue remained, caused by a different synchronization operation, an MPI all-reduce call. The sawtooth pattern shown by MAP is also typical of an imbalance operation, in particular when the workload depends on the process rank. Again, optimizing the imbalance bottleneck consists in optimizing the computations that cause the other processes to wait. This will turn the teeth of the saw as steep as possible. If we increase the number of steps of our application, a new bottleneck appears. We can spot occurrences of a checkpointing function where data are dumped in a file in order to restart the simulation at the same point if the job stops. Often, when it comes to load balancing, the costliest function shown by the profiler is not the bottleneck, MPI barrier in this case. Instead, the bottleneck is the cheapest function, here the sequential I/O write. For I/O operation, prefer the use of an MPI I/O function, which will perform parallel I/O instead. The problems we have listed earlier also appear with OpenMP or hybrid application. Again, MAP can help investigate on the source code. The interface slightly changed in order to identify single-threaded sections of the code in dark green, multi-threaded sections in light green, and OpenMP synchronization in gray. OpenMP has similar features to the MPI function we mentioned earlier, barriers and reduction. But one difficulty corresponds to implicit barriers, in particular the ones which may appear at the end of parallel loops, such as what is shown on the screen. To optimize this, pay attention to the loop scheduling. Dividing the work in equal chunks is the best way to avoid threads waiting for others. The last but not least, memory imbalance can affect the scalability of your application. Again, MAP can help diagnose the issue by displaying the memory usage among processes over time. On the screenshot here, you can see that MAP reports that the memory usage of the application increases to a maximum of 1.2 gigabytes for rank 3 of the application. This causes the application to crash because of memory exhaustion when scaling up. To fix it, a parallel debugger like ARM-DDT, also part of ARM-Forge, is the solution. ARM-DDT aggregates and simplifies the complexity of HPC applications and allows developers to play applications step by step, investigate variables, array and communications across processes with a reactive and user-friendly interface. When executing the application, the user can display memory usage, even at large scale. DDT shows readable graphs indicating which processes allocate most memory and what are the top allocations to track the root of the problem. In this case, DDT displays the memory imbalance between rank 3 and the others clearly, thanks to the pie chart on the top left corner. We can identify process number 3 allocating about 1.3 gigabyte of memory when the others only allocate 250 megabytes, something we already knew from MAP. On the right, the histogram displays that the packet allocate function is responsible for the main allocations for rank 3, but also for the other ranks. A right-click on the corresponding area of the histogram gives the many allocations performed since the start of the application and a line of code where they occur. Fixing the problem becomes an easier job. To conclude, I hope you understand better now how the ARM HPC tools can help you identify and fix imbalance in your application, whatever the underlying architecture, whatever the scale. It provides everything a scientist, a developer, an expert need for the latest technologies, and it maximizes the efficiency of HPC systems. If you would like to follow up and know more about our tools, here are a few pointers to documentation, tutorials, previous webinars, and to request a trial license. Thank you very much for your attention. I hope you enjoyed the webinar. We are going to start the Q&A session, so if you have any question, please feel free to ask.